One of the most glorious things about the internet is that no matter what you're interested in, you can find other people who are interested in it too. Myself, I'm a nerd. I like all things nerdy. You should really expect this out of a math teacher, but if, for instance, I want to go online and find t-shirts that are funny and nerdy and represent to other nerds that, hey, I'm one of you, I can go find things like this, a t-shirt which has this design on it that explains the rules of rock, paper, scissors, lizard, Spock. Which, if you don't know what that is, it's an extension of the game rock, paper, scissors, adding 2 more things in there. Kind of funny, really awesome. Happy to explain later. But more importantly, I can buy these t-shirts to signal to other nerds that I too am a nerd for $20 a piece. And my question is, of these 2 graphs, which one of these better describes the situation of buying t-shirts for $20 each? In this video, we're going to be describing intervals of domain and range using inequalities, and we're going to see what situations require the use of inequalities rather than just a list of numbers like we've been doing. So back to this graph. If we look at this, there is a definite right answer here. If I'm going to describe this set of data, answer choice A is what I'm looking for. I would not use B to describe this situation, and here's why. In B, I've got this continuous line, this line that goes on forever, as opposed to just points in A. And I can look at, let's say, this point right there on the graph. That's the point 0.5 and 10. But those numbers have actual meaning. 0.5 is my number of shirts. 10 is the cost in dollars. Well, there's nothing wrong with $10. We can do that. But there is something distinctly wrong with the idea of buying half a shirt. That's not something that can happen. You either buy 0 shirts or you buy 1 shirt. There's no in between. And so my data should look like this, where I have these jumps. These 2 types of data sets are called discrete, where we have these jumps in between, and we have what's called continuous data, where there are no gaps in between. And so we're going to look at situations and that are discrete and continuous and look at what type of information is necessary, let's say, to describe the domain and range. So let's start with discrete data. It's a set of data in which the numbers can have only certain values. So that would be a situation like this. We're not allowed to buy half a t-shirt because that doesn't make sense. And so when I list the domain on these, I can list the domain as just a series of numbers. 0, 1, 2. And the domain can only have those certain values. They're not disconnected, so I don't have all the numbers in between there. It's just this right here. Continuous data, on the other hand, it's a set of data in which the numbers can have any value in a certain range. So if we look, I've got a graph here of the number of years you've been alive versus your age. And so what we see is that, yeah, we can have those points that are easy to read. If you've been alive for 1 year, you're 1 year old. After you've been alive for 2 years, you're 2 years old, and so on and so forth. But it's also very possible to have those in the middle. You can be 1.5 years old. That's legit. You can be 2.9 years old. In fact, there's no number that we can pick in between here that doesn't work. So between 0 and however far up this goes, we can have any value in that range. And so when I go to describe the domain, if I were to try and describe that like I did for discrete data, I would have to start at 0 and list literally every number in between 0 and wherever this stops. Now, because we can continually put smaller and smaller points in there and add more and more decimal places, it turns out there are an infinite number of numbers in there. So it would take longer than the lifespan of the universe to write those down in that form, which means we probably ought not do that. So instead, when I have a continuous function, not a discrete function, but a continuous function, we describe that interval where the function occurs using an inequality. So let's look at some examples. describe the domain and range of this function, and I can see this is a line that starts at 0 and works its way up. The arrow at the end is important because that means this thing will go on forever. And so what we're going to do is we're going to describe the domain and range of this using inequalities. And I'm going to use a bit of a graphic here to help you kind of understand what's going on. So what I'm going to do to find the domain is x values, so things along this x-axis. And so what I want to do is I want to start on the left, and I want to figure out where the graph starts on the left. And you can see it starts right there at 0. And so I'm going to block it off because I don't care about anything that happens until we get to 0. Now, where does this stop? On this side. Well, it's got the arrow, so it goes on forever. So it never, ever, ever stops. It keeps going forever. And so I can think of this as just like we did before on the x values, or on the x number line. It's like I'm shading everywhere along that number line, and it goes on forever. And in fact, if I look over here, it can be 0. Hey, why don't you skedaddle there, box? Thank you. It can be 0. We're still talking about age and the number of years you've been alive, so 0 is an option. And we can see from that domain that we have the domain x is everything greater than or equal to 0. It's like we just shaded this in on the number line. We can absolutely do that. And then we can do the same for range. I'm going to mix up the colors on this so that we can keep that separate a little bit. But we can do the same thing for the range. Let's take a box and let's draw, or let's block out here where this starts. From the bottom, it starts right here, and from the top, it never ever stops. It's going to keep going. And so our range on the y-axis is everything greater than 0. And so I would write that my range is y is greater than or equal to 0. And so those boxes just help us narrow in on what's actually important there. And so I can see the domain, the possible x values. Every x equal to or bigger than 0 is a possibility. That line has a point on it somewhere with every x value greater than 0. Same thing for y. Somewhere on that line, there is a value of y for every number greater than or equal to 0. And that's what I mean by domain and range of a continuous function represented by inequalities. Let's take another one. So here I want you to describe the domain and range. So let's look at the domain first. And just as I said before, let's think about this as blocking off from the left side. Run this across until we find our function. Hey, there it starts, or not function in this case. And then over here, where does it stop? Well, it goes until right there. So we can see that our domain is really just everything from 0 out to 4. And if I move these guys out of the way, I can kind of see now whether the ends are included in that. And for this, remember everything you knew about inequalities. Here it does touch 0, so that's like a solid dot. Over here they're open circles, which means it does not get to 4. 4 is an open circle, and so I now need to describe all the numbers between 0 and 4. So here's how I do this. I'm going to take 0, and I'm going to take 4, write them like this. X is in between. X has to be greater than or equal to 0, but at the same time must be less than 4. It's a compound inequality that describes that area in between. And now I can do the same thing for my range. For my range, I'm going to look at blocking off everything from the bottom. So I start from the bottom and find where my function starts, or my relation, I should say in this case. And then from the top, where does it stop? Right there. And so I can see my range is everything in between 2 and -2. And if I get rid of these guys now, I can start looking at what happens at the ends. Here it's an open dot, so 2 isn't included. Down here it's an open dot, so -2 isn't included. And I just have to describe that collection of numbers on the number line. So again, I start with my smallest number, end with my biggest number. Range is represented by y. So my y value is bigger than -2, but smaller than +2. And there we go. I've represented the domain and range of this function using inequalities. So here we've got this one, and we can see now that this thing doesn't have to be usual or pretty or what we think of as a quote-unquote normal function. In order to do this, I'm going to start by looking for my domain, and it's the same thing. I'm going to take and look at where it starts on the left side, right there. And I'm going to look at where it stops on the right side, right there. And so my domain is now everything in between that. And now I can take these away and kind of look at what's going on those ends. I say I can take these away. Let's see if it actually works. And I look over here at 1, that's going to be an open circle. It's not included in the graph. Over here at 4, it's a closed circle, so it is included. So my domain has to be between 1 and 4. Domain is represented by x. It has to be greater than 1. Oh, I seem to have lost my pen. It has to be greater than 1, but not equal to, because it's an open circle, and less than or equal to, because it was a closed circle, 4. Now I can do the same thing for my range. Let's look at this in terms of where it starts on the bottom. Starts right there. And where it goes to up top. Notice that it doesn't have to be the ends. I just want whatever the topmost piece of this function is. So I'm sort of setting up these two orange squares to box in my representation. Like all of the graph has to be in between those two boxes, either up and down, left or right. So in this case, all my y values are between -1 and +1. And now I can skedaddle these out of the way. We can talk about what happens at those ends. Here, it's a solid line, so 1 is included. Here it's a solid line, so -1 is included. And so I would say my range value, think about just describing this here. If it helps, you can almost think about turning your head sideways and kind of looking at it that way. But the range is between -1 and 1, and it can be equal to both of those. So I say that y is between -1 and 1. One final example, I'm asked to find the domain and range of this bad boy. So we do it the same way. Let's block off our two ends using these boxes here. So I look, my function starts right there at 0 and goes forever. That arrow means it keeps going, so it never stops on this side. And so my domain is everything going forever that way. So let's get this guy out the way and come back, pen, come back. So our domain, this is an open circle right here. So our domain is everything where x is greater than 0, and it goes on forever. Now for my range, I'm going to box in from the bottom where it starts, but that arrow means that it goes forever in that direction, and so my y value is just everything from there. That is an open circle down there, so 0 is not included in that either. So I would say that my range y is greater than 0. And excuse me, I notice now that I've got my wrong symbol there. That should be x is greater than 0, pardon me. And so I can see that the domain is just all the possible x values, the range is just all the possible y values. It's just that because there are an infinite number of them, I have to list them as inequalities. So remember, let's scoot back through this double time. I have two types of data, discrete and continuous data. For discrete data, that is data that when I draw the graph, I have to pick up my pencil. For discrete data, I can write the domain as just a list of disconnected numbers. But for continuous data, data that is a solid line where any value is allowed, I have to write my domain as an inequality. Good luck.